Okay, thanks for the introduction, and thank you for inviting me here. It's a great hotel and a great conference. So today I'll talk about the correlated variable selection, which I've actually talked to several of you during my poster session. So I think maybe I'll add something new to who have taken my poster already. So if time permits, I'll talk a little bit about online learning. The first part of my talk actually has a very close relationship to the talks we heard yesterday. In particular, I think Carl, I'm not sure if he's here or not. I really enjoyed his talk, and the idea actually is related because he used preconditioning to address the issue of correlated variables when you apply lasso type of methods. So I will use similar ideas, but in a very different framework, in very different ways. And we apply to both regression and apply to classification. And as I mentioned before, I also talk about Bayesian online learning. Basically, how do you apply Bayesian models to do inference on nonlinear dynamic systems? Okay, let's start from the first one. So in this figure, basically, it's a design matrix. You have a lot of variables or features, and you have a few samples. So P is much bigger than n. A motivating example for what I'm doing is this figure. We have two variables, x1, x2. They're not correlated as shown in the figure. Basically, the two classes, blue dots and red triangles. If you apply lasso, you basically got a vertical line that will separate these two classes perfectly. Okay. So what's interesting is, suppose there's a strong correlation between them. Like we see in this figure, you can see x1 and x2 are linearly correlated. For example, this could be gene co-regulation and other possibilities. In this case, if you apply lasso, you basically will choose x1 to separate the two classes. But then for many applications, actually you do want to have both x1 and x2, like genes, cofactors, or maybe SNPs that are strongly correlated. Well, you can say maybe we can apply group lasso or elastic neck. So the idea is we use different penalizers. This figure we see this many times yesterday already. I just added last night to draw the connection to all the talks we saw before. We have a feasible set, and if you have data likelihood, the solution will be likely there, the red star. That will be the sparse solution. Well, see, we can make it less sparse to do group selection. Basically, we use a composite regularizer. That's to say combination of L1 and L2. Therefore, we will have a selection of both x1 and x2. You can have many other variants like SCOT and so on. But all these regularizers essentially are just changing the shape of regularizers, have different properties, consistent properties, and so on. But they actually ignore the correlation information in the data. So in one correlation, basically the eigenstructures. So yesterday we heard we can use preconditioning to bypass this problem and make lasso works beautifully again. But the DDLC actually can do differently, and also you can apply to a variety of problems. So we call this method eigennet. The idea is we're going to use eigenstructures, eigenvectors to guide your variable selection. But at the same time, you're going to use the label information to choose the eigensubspace. So you have a double selection here. For those familiar with graphical models, here's the graph. Okay, if you don't like a graphical model, look at the left-hand side. There's one equation there. Basically, this is a classification model. You have a data input xi. You want to do a classification or regression. Y is the label response, and you have a classifier w or regression weight w. And you can plug in the different sparsity prior, say L1 prior or ARD prior. So this is nothing new here. Everybody knows it. Now we're going to introduce another model, which is a generative model. In this model, we have latent variable W tilde. And this W tilde is a constraint in a subspace. This actually is like a PCA. Basically, the W tilde is a constraint in the eigensubspace, Vj. Vj are eigenvectors of the design matrix. Basically, have many eigenvectors, then we say Wj belong to this eigensubspace. But unlike what we heard yesterday, instead of using all the eigenvectors to say decorrelate variables, here we actually introduce an additional variable Sj. The Sj will say Instead of using all the eigensubspace, we only use some of them because some are useful, some not useful. So how do we choose which one is useful? We glue the conditional part, which is a conditional classification model, with the generative model together. In this model, then the information from from label information Y will help you to estimate the latent variable S. That's the selection variable for the eigensubspace. And in return, you also have a selection from you also have a guidance from eigenvectors to help you select the individual features. So really the two-way traffic in the model. So for those of you who really don't have a much preference over graphs, we can show a graphic model. We can show you interpret this model from the classical perspective. So this is when we have uncorrelated variables, the eigenvectors are parallelized to the axis. So the solution, as I showed before, actually is a constraint in the eigensubspace. Then when I uncorrelated the V, the eigenvector will basically parallelize to the vertical axis. The solution will be sparse again. So you're back to lasso as before. But when you have strong correlation between variables, the solution is dragged by the eigenvector towards another location. And then you have a non-sparse solution. So this is really kind of like adaptive composite regularization. So when variables are uncorrelated, you have a lasso type of behavior. When they're correlated, then you adaptively change it to another domain. Okay, but this is for 1D, for two-dimensional space. Only I show you one eigenvector. When you have many of them, we actually also use the data likelihood to choose which eigenvector are useful. Okay, basically we are learning the subspace as well. So you can view this as a combination of say, classical sparse learning with PCA. But we're learning the subspace for PCA. So let's back to the simple example we studied before. The two variables are not uncorrelated, then you have a solution for lasso and your eigennet. They're identical. There's no difference, really. But then when you have strong correlation between them, then our solution is this way. The bold line is the eigennet. You can see it's very different from eigennet solution. We'll choose both variables. And actually, empirical results also show that. Some synthetic data, when you have no correlation between variables, the x-axis is the number of training examples, y-axis is the test error. The smaller, the better. In this case, you can see all the methods are pretty much the same. There are not much differences. But when you have strong correlations, basically we have two variables are related. We have out of 40 predictors. Actually, 8 variables are related to the label. Then we have two groups. Each one has 4 correlated variables. In this case, you can see the new method eigennet achieve much lower prediction error than competing methods. And then I'll show you the regression weights. So this is I didn't show the ground truth. Basically, we have 4 group 1, group 2. 4 are correlated. One group 1, another 4 are correlated, give the negative contribution to the prediction. You can see lasso and ElasticNet give you over-sparsification. Actually, if you tune the weights for ElasticNet, you can make it denser. But you will not have a sparse solution for the variable 0 to 30, but then you have a dense solution for variables, say 30, 32 to 40. So you're sparse in one range and then you're dense in another range. And we cannot really do this based on, say, traditional lasso or ElasticNet because it's basically a global regularizer over all the variables. You can also view this actually as an adaptive group lasso, really. Essentially, the groups are defined by the eigenvectors, by the eigensubspace. But also, we are learning that with the data-driven groups, we are learning the group automatically from data. And also, we are learning the importance of individual groups. So if you do a group lasso, we have regularization coefficients for individual groups, but how do you learn that? So in a Bayesian framework, actually in empirical Bayesian framework, we learn all the parameters associated with individual eigenvectors. Then we apply to AD studies. This is real data from Alzheimer's disease initiative. So we have SNP data. Actually, the SNP is much higher dimension. We basically do a pre-filtering to get top 2,000 SNPs. Then we have about 400 subjects. You can see our method achieve lower prediction error than competing methods. The error bar, this is average over 10 splits, and the error bar indicates standard error. Then we do the same thing, but now it's on regression task. So that's based on the ADAS QUAG score. Basically, measure how good you are in terms of memorizing your history, your past, your cognitive capability. The same pattern we see here. The reason actually not surprising because for SNPs, there's a strong correlation between all the genetic variations. So in some sense, actually, that's what we expected. In this part, I assume I have no idea about I have no additional information besides the design matrix. I basically learn the eigensubspace and I use it to guide the selection. But in many scenarios, you do have additional information. For example, for many biological applications, you have also pathway constraints. You know, gene A regulates gene B regulates gene C, and so on, or maybe AB co-regulates another gene. So this type of relationships can be represented by graphs. So you have many, say, graphs, and you basically have a network. Now the issue is, can you tell me which sub-network is useful for the prediction? Or maybe not the whole network for each individual one, but also you want to select individual nodes from the graph. So this is a joint graph and node selection problem. And we come up with a new approach to do that based on Bayesian framework. So we call it nanos. My student name it. It's called network and node selection. I forgot what's O for. Basically, you select both networks and the nodes from the data. You will basically represent the constraints, the pathway graph constraints by graph Laplacian, but we embedded in a generalized Spark slab prior. So yeah, Spark slab prior is a very good prior for variable selection in a Bayesian, actually proposed in Bayesian literature. In our contribution is basically generalized. This prior introduce additional constraints to couple the selection variables together using graph Laplacian. Then we actually have two levels, just like the work I talked about before. We have both selection of variables and also selection of networks. So there are really two-level selections. So I'll skip the details, and that's the results. On synthetic data, we'll apply again to regression and classification. You can see the new method give you lower prediction error. So for both regression, that's A and C. The lower the better, that's the error. And on the right-hand side, I'll show you the selection accuracy. That's the basic product recall and accuracy, recall and precision. This is basically defined the F1 score. So the higher, the better. You can see we give a better, not only prediction error, not only prediction accuracy, but also higher selection accuracy. This is synthetic data because we know which features really contribute to prediction. We can evaluate this accuracy in terms of selection as well. So here we compared with Lasso ElasticNet Spark slab with the classic, actually with variational inference. For this one, the Gibbs actually gave worse performance because it's just being slow. We also tried group Lasso because here I just say I ignore all the relationship between variables. I just treat it as a group and run group Lasso. And also we compared LL method is a graph Laplacian-based variable selection. Okay, so that's this figure. Now apply real data to cancer studies. So we apply to 3 real cancer study data. Basically show you, again, lower prediction error. Then we have lots of biological analysis in our bioinformatics paper. You can read more details for the biological part in the paper. Then we apply the same trick, same idea to AD study, again for Alzheimer's disease. And in this context, we compare the ARD, that's a Bayesian variable selection method. Again, but here the constraints is not a pathway constraints, but about symmetric constraints. Basically, we say the left and right-hand side of the brain should be symmetric. And most of the selection should be happening on both left-hand side and right-hand side if we have MRI data. But we also say sometimes they are not symmetric. Then we will use selection on the constraints and also on the individual pixels of the MRI image. So you can see a dramatic reduction in error rate here. So ongoing research is about multi-view learning in our group. So now we generalize this. We say, well, we want to do both imaging data and SNP data, and I want to predict the disease status of the 3 sources. So we want to learn the connections between all of them. This can be viewed as a CCA model, canonical correlation analysis. You basically want to find out association between two sources, find out which genetic traits, which genetic variations associated with, say, shrinkage of hippocampus. and how they contribute, say, link to the Alzheimer's disease diagnosis, say, normal or MCI or AD. MCI stands for mildly cognitively impaired. This work actually is also has very strong connection to the previous work actually here at Duke. And you guys have a lot of work on the sparse latent factor model. Actually, they're very, very similar. I would say the main difference is currently we actually add local factors on individual views. So not only one factor to explain both views, but we also have latent factors only for image and also only for the SNPs. So this is more like a classical CCA model. But this can also be viewed as supervised CCA because the label information, well, it's Gaussian process to predict the labels, and the label information can help you to guide the selection guide the dissociation study between the views. So how much time do I left with? 10 minutes? Okay. So then I have 10 minutes for another part I didn't mention at all yesterday during my poster session. Online learning. So in this part, the context is we have lots of data from many disciplines, from science, from engineering, from Amazon, from Google, or from financial markets. So how do we handle massive data? So one idea is basically instead of treating data as a batch, we process one data point at a time and pretend that it's actually data stream. But this actually also their classical setting basically is data streaming. Basically have a dynamic, they have data stream coming, one point coming at a time, and you naturally have a dynamic, have a time series data. So in machine learning community, we call it online learning, but you can also say it's basically dynamic systems. In a Bayesian framework, there are lots of work done along this line. Actually, Bayesian framework is very natural for dynamic system because the classical work, which is very famous, is common filtering. Basically, treat the linear system, you do filtering, you are done. You can also do it on hidden Markov model. It's a discrete version of the same model, but you can just do message passing. So now this has been unified in a framework called factor belief propagation that will unify common filter and HMM inference in one generalized algorithm. They have many versions of generalization of common filter, extended common filter, uncertainty common filter, particle filter, assumed density filtering, and so on. There are many, many versions now. When you have nonlinear dynamics, for which you cannot apply classical common filter. In machine learning community, actually, we have another line who work on the same, almost identical problem. So we have stochastic gradient descent. It's become extremely popular. If you look at ICML processing or NIPS, there are maybe 1/3, more than 1/3. Besides deep learning, 1/3 is about apply stochastic gradient descent to whatever model you have. And they then say, oh, we really scale up the problem. The idea is fairly simple. Instead of compute gradient on the whole data set, I'll compute gradient on one data point and keep doing this again and again. And there are many nice theoretical results that justify why this makes sense. Then there are the extension, like a natural gradient, basically doing gradient descent on a manifold. This can also view from traditional ECE perspective as an information scoring method. You basically score the metric, you define information geometry by the Fisher information. Basically, the Fisher information matrix is the kernel, is the metric for the information for the manifold. You basically move the gradient along the manifold. And this actually is called natural gradient in machine learning community. Then there's online Gaussian process work, Gaussian online GP work. This is basically using its generalization. It's basically using assumed density filtering. You project the distribution in the particular family. You do that again and again and again, and keep doing it. Then you have essentially you have the key is projection. Basically, project a crazy distribution into a particular family. Within this work, they project into Gaussian process, actually parametric form. Then there's also online SVM, it's called passive-aggressive algorithm. So all this method, essentially, you have like a parametric summarization of the history. In Bayesian framework, often it's summarized all the information in exponential family. It's a Gaussian or something else. That's what you want to do. But we can do something maybe more interesting. Well, that's basically look at the history. Intuitively think of how do you define your life trajectory. Maybe it's heavily influenced by a few key steps. It's like only few steps to define where you are and what you're doing now. So let's say maybe you can generate some virtual points to summarize the history, and we dynamically update them. that summarize the whole data stream. So there's a similar idea appear in actually in the online in data streaming literature. It's like data sketching, data summarization, and so on. So now we're putting very concrete context, say classification. Not all the points are critical to define the decision boundary. Only few are more important. Or maybe many points, many events are very similar, give a similar impact. You want to group them together. Okay, so it's like summarization of data. In the Bayesian framework, we're going to implement this idea basically in the principled way. So this is really summarization. This is really combination of data summarization and the parametric projection. So in this work, we have I skipped that part. Basically, we have a joint posterior distribution of a dynamic system. That's what you want to do. If you apply common filter, that will give you a solution for that. But for nonlinear dynamic system, you cannot do it. So how do you do it? How do you handle that? We basically project the PW given data into another distribution we call QW. QW has the parametric parts, RW, that's the Leibniz exponential family. For example, Gaussian, okay? Then we have additional term that would be the product of F for BIW. So it's like these are virtual data points. And the BI will be, say, virtual data points. By putting them together, you summarize the whole data history. That's the idea. Now you can see the QW is not in an exponential family anymore. It's actually a crazy distribution. I'll visualize it in a moment. So the projection part, we know how to get RW. For example, we just assume density filtering. Now the art is how to get a BI, the virtual data points. So for classification, we use two ideas. So one is, say, deletion, one is merging. Okay, let me visualize that. Very simple. Given three data points, we have decision boundary. Really, this is, okay, this line separates the red dots from the blue square. Now, what if we have additional data points? This one, the third data point. You can see probably that data point doesn't have much impact on the decision boundary. Actually, for people like SVM, you see this immediately because the red dots are corresponding support vectors. They have the third point has no impact on the decision boundary. Actually, from analysis, we call it, we define a Bayesian margin. That's the quantity formula show up. So that depending on the mean and the covariance matrix occur in the posterior distribution. If far away, then we basically delete it. You can also view this from a geometric view. We visualize the posterior distribution actually in a bizarre way. For people from AI, it's maybe more familiar with. So, for example, a Gaussian distribution, you can think about it as a ball. It's in a log domain, it's a ball, okay? It's a quadratic. Now we have a data point, say just step function, okay? Not a logistic function, just step function. You're cutting the ball each time. One data point, say on left-hand side, it will all be pruned. Only right-hand side will be kept. If another data point comes in, you're going to cut the ball again. Another data point comes in, you're going to cut the ball again. Whatever left will be the mass in the posterior space. Basically, the posterior will corresponding to the common space, remaining space after all the hyperplane cutting. This also in the AI literature known as the variance space. Basically, that contains all the hypotheses consistent with the current constraints. But now suppose the 4 data points correspond to 4 hyperplanes. You can see the fourth one is the pink one. Really has no impact on the red variance space. That's the red part of the variance space, the posterior space. So we can say maybe you can just remove it, okay? Now we'll have 2 data points, like 2 blue points. We're talking about merging now. Well, I can say just move them together. They're very similar. So that's what we see in this figure. You have variance space, that's the red area. Now I have 2 data points correspond to 2 planes. Merging them together, a third one, but you can see overall they're very similar. So that's basically the idea behind this algorithm. Then we actually generalize this assumed density filtering by using an idea called virtual, actually inverse ADF. We will find one point that give you same impact when you project 2 data points into a small space. We do it recursively. And that's the accuracy. We compare ADF, using only one data point, just doing filtering. And our new method called virtual vector machine, using a few summary data points. And the EP, that's basically batch learning. We use all the data points and do the learning. And of course, that's the most accurate approach you can do for deterministic inference I'm talking about. Then you can see that the smooth transition between EP and ADF. Okay, the price you pay is the additional computation. Basically, you have a buffer. You say, my cell phone can only save, we'll say, 5 data points for this whatever application. Then I will choose the corresponding, say, B, the size of the buffer, the size of virtual data points. Then apply to, say, online learning. So apply the classification problem. We compare to variety of methods. Online Gaussian processes, online SVM, natural gradient, and ADF. And you can see the fast convergence to the lowest error rate. So x-axis is number of training points. Y-axis is the error rate. The lower the average error rate, the lower the better. Okay, so let me summarize. So I talk about 2 scenarios for Bayesian models for data analysis. So one scenario is we have lots of variables. It's a high-dimensional problem. Another scenario is when you have a lot of data points. Basically, that's the 2 cases. For the first case, the main issue we're addressing is the correlation. We have correlation between variables. How do we deal with it? So we either use a data-driven approach. We learn the eigen subspace, or we use additional information represented by graphs to guide your variable selection. At the same time, we'll select the constraints or graphs of the eigen subspace. And we also apply this can handle both regression and classification problems. For online learning, really, we combine this parametric approximation like EP or other ADF with online data summarization. You can view this as clustering, really. It's giving new data point, I'm clustering a bunch of data points together throughout the data points. But then I have actually a non-distribution that's not an exponential family. You have a nice representation posterior. It gives you very good trade-off between computational cost and approximation accuracy, basically user-defined. So in the end, I want to thank my group members, actually who did lots of work, majority of the work, and my funding agency for this work. Okay, thank you. Okay. Okay. Yes, this actually was inspired by data squashing, right? Instead of squashing, basically you have data likelihood, you combine them together, right? Yes, it does have a similarity. But the difference is we're doing it by preserving the posterior distribution principle is different. We're also doing an online version. The high-level idea is similar. It's actually like squashing, yes.
So can you maintain the variance?
Yes, we're maintaining the variance. That's the key idea. We basically, the idea, how do we choose which one to throw away, which one to merge, is based on we try to maintain the uncertainty, the variance. That's the idea. Yeah. Okay.